All right, let's jump right into this explainer and explore how modern data processing has completely evolved. We've moved from these rigid, clunky factory lines into continuous, fluid pipelines. Today, we're going to unpack the fascinating world of data flow engines. So if you've ever wondered how tech giants manage to process absolutely endless streams of data without skipping a single beat, well, you're in the exact right place. Here's a quick look at our roadmap for today. We're going to start with the MapReduce bottleneck, then move into data flow engines, directed acyclic graphs, operators and parallel execution, scheduling and fault tolerance, and finally, we'll look at some real-world ad analytics. Starting things off with Section 1, the MapReduce bottleneck. To really appreciate where we are now, we have to look at this stark contrast in data philosophies. On one hand, we have the traditional MapReduce approach. Think of it like a highly rigid factory that painstakingly packs up every single one of its subassemblies and ships them into a massive warehouse, in this case, a distributed file system, before it's even allowed to take the very next step. On the other hand, you have the Unix pipeway, where processes just seamlessly and incrementally pass items right down the line the second they're ready. So the absolutely crucial point here is that this strict MapReduce requirement, having to write all your intermediate state to a hard drive, creates a massive, massive bottleneck. A job can only start when every single task in the preceding job is totally finished. If just one machine in the cluster is having a slow day, what we call a straggler, the entire workflow just literally grinds to a halt waiting for it. Plus, writing to a distributed file system means you're copying that temporary data across several different machines, which just adds a huge amount of totally unnecessary overhead. Which brings us nicely to Section 2. Enter data flow engines. The core shift in thinking here is treating the whole process as one continuous modern assembly line. So instead of breaking a workflow up into isolated, independent jobs that barely talk to each other, a data flow engine steps in and handles the entire process end-to-end as one single job. It looks at the whole picture, pulling data through the system smoothly without constantly slamming on the brakes to put things into cold storage. Let's look at the blueprint for this. Section 3, directed acyclic graphs. In data flow engines, you don't just blindly pass data forward and hope for the best. You actually map out the exact flow of data from one operation to the next as a graph. It's called directed because, well, the data flows in a very specific forward direction, and it's acyclic because there are no endless loops. By explicitly declaring all these data dependencies ahead of time, the system's scheduler gets this incredible bird's-eye view of what data is needed, exactly where it's needed, and when. And because the scheduler knows exactly what the whole graph looks like, it can optimize the process dramatically. It can actually place the task that consumes data on the exact same physical machine as the task that produces it. That means they can share data straight through memory instead of dragging it over a slow network. It avoids those redundant mapping tasks that totally plagued MapReduce, and crucially, it enables pipelined execution, meaning operators can just start doing their job as soon as their input is ready. No more waiting for the whole previous stage to finish. Moving along to Section 4, operators and parallel execution. Rather than forcing every single step into a really rigid map and reduce cycle, data flow engines rely on a much more flexible workforce using generalized functions called operators. You can chain these together literally however you want. You can filter, then join, then group by key. Really expensive work, like sorting, is only performed when it's explicitly required by a specific operator, like a sort-merge-join, rather than just happening by default at every single step of the way. Now, even with all this flexibility to handle massive scale, data flow engines still heavily parallelize the work by partitioning data. For instance, user activity logs and user database records are processed in parallel. The system simply extracts a key, say a user ID like 104 or 173, and it routes all records with that exact same key to the same specific partition. This ensures multiple nodes can process massive inputs simultaneously while still bringing related data perfectly together. Okay, but what about when things go wrong? Section 5, scheduling and fault tolerance. This is absolutely vital. In the old MapReduce days, we saved every single intermediate step safely to a hard drive. So if a machine crashed, no big deal, you just read the file from the hard drive again. But data flow engines keep things in memory for speed. So if we aren't saving to disk every step of the way, how on earth do we prevent a total failure when a node inevitably goes down? The answer is actually pretty brilliant. It comes down to smart recomputation. Systems like Spark use resilient distributed datasets, or RDDs, to track the data's ancestry. The framework essentially remembers the exact recipe for how a given piece of data was computed, which input partitions it used, and which operators were applied. So if a node crashes and memory is wiped, the engine doesn't panic. It simply looks at the blueprint and recomputes only the specific piece of data that was lost, pulling from a prior stage or the original file. There is literally no need to start from scratch. Let's ground all this theory in reality. Section 6, Real-World Ad Analytics. Let's walk through a real advertising analytics pipeline. Say a user types a search query. That generates our first event. A few moments later, they click an ad. Boom, our second event. To figure out our click-through rate, we need to seamlessly match these two distinct events together. By grouping them by the same session ID within a specific time window, the Dataflow engine executes what's called a stream-stream join, calculating that click-through rate dynamically, completely on the fly. This scenario is perfect because it shows exactly why Dataflow engines aren't just for bounded overnight batch processing. When dealing with unbounded datasets, data that literally never stops arriving, the stream processor has to maintain state. It actually holds on to that recent search event right there in memory, just waiting for the related click event to arrive so it can immediately join them. It's incredibly powerful for matching up unpredictable events over time without constantly hammering a traditional database with queries. Finally, let's zoom out a bit. Section 7, the future of Dataflow. Software engineer and author Martin Kleppmann points out a massive advantage here. When you treat data pipelines as continuous functional transformations from an input to an output, your architecture just becomes incredibly robust. Because inputs are immutable, they don't change, and outputs are entirely derived from them. If you happen to introduce a bug into your system, you can literally just fix your code and rerun the data flow to recover. It's that simple. Ultimately, by embracing Dataflow, you aren't just moving static files around anymore. You are effectively unbundling the traditional database. You're subscribing to a living, breathing stream of state changes. Your application code starts to act exactly like a database trigger or a materialized view updater, creating this amazing network where the entire organization basically functions as one giant real-time database. So I'll leave you with this to think about. How could breaking down your rigid, siloed data storage into continuous, flowing pipelines transform your application today? If you stop waiting for tomorrow's batch job just to tell you it happened yesterday, the possibilities for real-time responsiveness are practically endless. Thanks for joining me on this explainer, and hey, keep that data flowing.